Hello everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 7.4 and we'll finish up the OpenCL host code so that you can begin to do your optional programming assignment on OpenCL. This slide shows the OpenCL host to device data transfer. So this is equivalent to CUDA mem copy from host to device. And like CUDA, OpenCL actually has two different kinds of API functions, one to transfer from host to device and one to transfer from device to host. This command, CL enqueue write buffer, is the API function for host to device data transfer. So all these commands are named with the host as the reference. So here the host is writing into the device memory. That's why it's called enqueue write buffer. And this function requires 9 parameters. The first one is OpenCL command queue pointer, and you have already seen in the previous lecture how we declare the command queue pointer and how we created the command queue in the API function that returns the command queue pointer value. So this is the place where that command queue pointer can be used. And the second one is the destination OpenCL memory buffer. And this buffer needs to have been created before we use the transfer function. And the third one is a blocking flag. This flag would tell the runtime system whether this command is blocking or non-blocking. If we set it to true, that means that the command will execute and finish before the runtime before the function will return. So if we set that flag to true, then this function will not return until the data transfer is complete. And we have the fourth parameter, which is the offset in number of bytes. So we're going to provide the pointer into the destination pointer in the OpenCL buffer, but we can also set a number of bytes into that buffer where we're actually going to write. So this is the concept of a sub buffer in a bigger device buffer. And we have the size of written data in terms of bytes. So we need to specify the number of bytes that will be writing starting from this offset location and onward. And then source host memory pointer. So this gives us the pointer to the host code location where we're going to be copying data from. And the list of events to be completed before the execution of this command. And this is related to the task parallelism that we discussed in the CUDA task parallelism section. So this is very similar to the synchronization command, but this actually allows the runtime to check on several other events that need to be completed before this copy can happen. So this explicitly express some of the dependencies that this particular command may have on other commands. And finally, there's an event object that tied to this command, and you can actually check this event object for for the status if you have a non-blocking data transfer. If you set the blocking flag to false, then you can use this event object to check later on whether the transfer actually has completed. And now we have the counterpart that does device to host data transfer. And this is called CL enqueue read buffer API function. And it requires pretty much the same 9 parameters. It's just that the role of the parameters are a little bit different because now the OpenCL memory buffer in the device is actually the source, and then the host is actually the memory pointer is actually the destination, and everything else is pretty much the same as the enqueue write buffer API function. So here we show a very simple example of how you can use the enqueue write buffer and the enqueue read buffer. So we can have if you want to transfer a 64 by 64 single precision floating point array, then if we assume that A is in the host memory that we want to transfer to device memory pointed to by D underscore A and vice versa, and we can use CL in queue write buffer and with all the appropriate parameters to transfer from host location A to device location pointed to by D underscore A here. And by setting the CL, the blocking flag to CL underscore false, then we make this command asynchronous. That is, the command will return right away, and then but it may or may not have completed that data transfer yet. So we can also perform a data copy from device back to the host by doing a in-queue read buffer, and we still use, we can copy the result, the data D underscore result back into the host underscore result. Obviously, you need to allocate D result and so on appropriately. So, but here I'm not showing all those details because by this time you know exactly how to create these pointer variables and allocate device memory as we have introduced in the earlier part of this lecture. So here we show a kind of a shortcut. Oftentimes, when we allocate a read-only memory, we also know that there is a host object that we want to be able to transfer into that read-only memory on the device anyway. So OpenCL gives you the option to use CL create buffer in a way that it will automatically also copy a host object into the newly allocated memory in the device. So we essentially will be able to perform the functionality of both the create buffer and in-queue write buffer in one API call. So this is an example where we use CL create buffer command, but in the device access flag, we not only say CL mem read only, but we OR it with another flag, which is CL mem copy host PTR. And you need to provide a valid pointer to a host memory area. So this is H underscore A here. And so then it will, the runtime will take this command and perform both the allocation and data transfer for the device memory. So here we show a very simple example that you will need to use for your assignment. So here we show the host memory pointers, and then we show the device memory pointers, and then we show the create buffer, which is the memory allocation for the device, and we show that we should allocate memory for read only on the device, but then we also provide the host pointer so that it will transfer the host A vector into the device device vector or device memory, and we do the same with the input B, and then we can allocate a buffer for results, which is C here, but we do not need to transfer because the kernel is going to be writing these results into the device memory. And then here we show how you can launch a kernel in OpenCL. Remember, we need to to have all the code sequence so that the OpenCL runtime will prepare the program and compile the program. So at this point, we have already finished the compile of the program. So that's I'm reminding you by listing this statement CL create kernel, and then we assume that the kernel function is going to be pointed to the pointer to that kernel function is going to be in this variable CL kern. So now we can actually launch the kernel. In OpenCL, launching the kernel is much more complex than CUDA. So in OpenCL, if we want to pass any parameters into the kernel, we need to actually use API functions to prepare these parameters. So here there's an API function called CL set kernel arg. So this function would need to have several parameters. The first parameter is the particular kernel you're setting the parameters for. That's CL kern here. And then the next one is the order of argument, or the particular position of the argument you're setting. So we're setting the zeros argument, first argument, second argument, and third argument here. And these are the arguments that we use to just list in the kernel function call in CUDA. So we also need to tell the runtime system how big each argument is. So this is the size CLM. Remember, CLM is the type of pointer to a data to a device memory location. So then we pass a pointer to the address of DA, an address of DB, and address DC as the actual parameter value. So finally, we also need to pass the address of the variable that gives the length of the vector. So these are the four arguments that we were passing into the CUDA kernel function. And here we just need to use four individual kernel argument setting functions to set these parameters into the runtime, and then we can launch the kernel. So the kernel launch is also a little bit more complex. So we declare a CL event, a variable event, and this event will allow us to actually wait for the kernel to finish before we copy the data back. So here we use CL enqueue ND range kernel. This is equivalent to the kernel function call. But here we actually pass the particular kernel that we would like to call, which is the second parameter in this API function. And the first API argument is the command queue that we're inserting the kernel call into. So then we have we're going to have several other parameters, and you should look at the CUDA programming guide for the detailed meaning of these parameters. But the important part is we need to have two variables that specify the size or the dimensions of the kernel in each dimension. So here we just we're launching a simple one-dimensional kernel, so we can just pass a variable where the G size and B size essentially gives the X dimension size of the parameters. And then we will have an address of the event variable that we can check in the next statement. So the next statement will have CL wait for events, and we're going to use that event. So that will allow us to wait until this whole kernel is finished execution. And otherwise, because this is an asynchronous kernel launch, it will come right down and it will go do the data transfer back. So here, this is how we can wait for the kernel execution and then go read the data back into the CPU. So now we're using the enqueue read buffer. And once we copy the data back, we can release the memory objects A, B, and C, DA, B, D, C from the device. So this completes all the conceptual background you need in order to write your OpenCL code for the optional MP. And for those of you who would like to learn more about the subject, I'd like to encourage you to read the OpenCL programming guide that you can easily find online, and also to you could finish reading chapter 14 of the textbook. Thank you.